Hello, everyone. We are Team 6, and we are going to present our framework Viral, which is variational inference for reinforcement learning. Before going into the framework, we would like to introduce the background for reinforcement learning. Reinforcement learning is a sequential decision making problem where the agent learns what actions to take to maximize a reward in the given environment, as shown in the corresponding figure also. For the project topic, we decided to replicate Viral, which is a variational inference framework for reinforcement learning that provides numerous benefits over existing methods. We will then investigate and extend Viral to multi agent reinforcement learning. We'll further improve the proposed approach by reformulating the residual error proposed in the main paper. So, first, we would like to introduce the background or the baseline that we are using maximum entropy RL, which is MERL, also called as SAC in the experiments. MERL promotes stochastic policies. More formally, the optimal policy is the highest expectation of the long term reward and the long term entropy, as shown in the objective below. It has various advantages. It promotes better exploration, it learns alternative ways for accomplishing the task, and lastly, it promotes better generalization. For instance, in the presence of obstacles, a stochastic policy can definitely perform way better. The proposed method Viral optimizes the following elbow objective. In particular, it consists of two steps of E and M by the actor and critic, where in the E step, we keep the parameters of our critic constant while updating the actor's parameters by maximizing the elbow with respect to theta. In the M step, we maximize the elbow with respect to omega while holding the parameters theta k plus 1 constant. Hence, the outer expectation is taken with respect to the posterior found in the E step by the actor. There are various advantages of Viral over MERL. MERL goes through time, and Viral is only dependent upon the current Q function. It doesn't consider the discounted future entropy into account, as you can see in the figure. At the beginning of training, the residual error is actually large, and therefore, the entropy of the policy is high, promoting exploration. In simple words, as error gets lower, entropy gets lower, and policy becomes more and more deterministic. There are various advantages of Viral overall over the existing methods. Naturally, just learns the optimal policy. Temperature is not a hyperparameter. Function approximator is explicitly used. Similar to MERL, stochastic policy is still used for training. Discounting is easily incorporated, and it optimizes the reverse form of KL, which is much more intuitive and useful in the reinforcement learning domain. For replication, the author code was available on GitHub. The code uses the Mujoko simulator, for which we had to secure the license for. The experiments are built on the existing reinforcement learning codebase in PyTorch called as RLKit. However, we found that the RLKit actually diverged from 2019 when the paper was published. And we actually had to walk through and find the compatible commits for running the Viral experiments for the paper. We replicate Mujoko V2 experiments on 3 tasks: Ant V2, Humanoid V2, and Humanoid Stand-Up. Originally, we expected to run into problems as the current version of experiments published on GitHub had a lot of bugs which crashed the experiments. So first, we started with Ant version 2. For Ant version 2, we reproduced the average returns similar to the paper for Viral and DDPG. However, SAC significantly underperformed the results in the paper. Then we tried Humanoid version 2. It was the most surprising task for us. The paper claimed that DDPG was the only algorithm that failed to learn, but to our surprise, only DDPG was successful and SAC and Viral failed to learn. Then we went for Humanoid Stand-Up. A Humanoid Stand-Up, Viral actually outperformed the results in the paper, but still, SAC outperformed the paper results again by a large margin. For all the experiments, we tried a lot of hyperparameters and different random seeds, but we still got better performance for SAC and DDPG for various experiments.
We ran into multiple difficulties as we were re-implementing this paper. For one, the author's code did not run as published. So the code they have provided on GitHub calls methods which don't exist in the class hierarchy, which means that the code that they have published could not have been the same code that was used to do the experiments in the paper. And the Docker file they provide does not have all the dependency versions listed as well. And there are many things which are very sensitive to the version, including Gim, MujoCo, and RLKit. So we had to go through each one of those libraries manually to find Git commits from about 2 years ago that were compatible with the version of code they have. And we're still not confident that we have the exact right ones, but we have ones that kind of work. So the paper does not list all necessary hyperparameters. For instance, here n sub epsilon is a KL scaling term, which is not mentioned. And there's also many other options, like Boolean options within the algorithms, which are not mentioned anywhere in the paper. And many of the algorithms perform differently than stated in the paper, meaning that at best, some of their results are underreported and the baselines actually do better than their experiments in the paper. So we tried to contact each of the authors on GitHub. One author told us to ask the other author, and the other author gave us a short and uninformative response and then went completely silent. So we also followed up with each author via email, and they were likewise unresponsive. So this is unfortunate because there are many things we would like to discuss, and we're actually really interested in this work. Another problem we ran into was computational cost for reproducing the experiments. So each experiment in MujoCo takes about 10 to 30 GPU hours, and we managed to run 3 environments on 3 models. So that's 2 baselines plus Virel, and that took an average of 11.02 GPU days, which is about all we could handle in the time frame between the presentations. So for improvements, we are extending this to multi-agent reinforcement learning, where multiple agents have easily learnable dense rewards for specific tasks and difficult sparse rewards for the overall task. So the solution we want to propose is to utilize Virel to create a multi-agent Virel to take advantage of the superior exploration behavior of Virel while learning. So in multi-agent evolutionary RL, which is the paper cited in this slide, each dense microagent has a shared set of MLP layers, its own head layers, which are independent. And each agent maintains its own separate replay buffer. So while each agent optimizes its own reward, the whole team is periodically perturbed, and the highest performers are globally selected for the next generation. So in this slide, we would be using Virel for each of these independent agents here. So there are 4 environments from this paper which we want to apply Virel to, and that is predator-prey, physical deception, keep away, and a rover domain. So another study that we want to perform is a study on error norms. So in the paper, they defined the residual error as having a generic norm, but as far as we can tell, the code implements a 2 norm, and there are no oblations of studying what the different norms or what effect the different norms may have on the final results. So we think that in a varying dimensions of the environments, the norm could have separate effects, and it might turn out to be an important parameter that needs to be set. So here is our schedule. So far we have finished the reproduction, and we are currently working on the improvements, and we hope to finish the project ahead of schedule, and we will see you at the next meeting. So thank you for listening to our presentation. Bye.